Okay, so far we've learned how to multiply our complex numbers and divide our complex numbers. So today's lesson is focusing on how to raise our complex numbers to some power, which sounds kind of complicated. Like every time that we square something or cube something or do something to the fourth power, things get more complicated. Like think about x plus 2 quantity squared. You can expand that out by multiplying those things, or x plus y or x plus 2 quantity cubed. All of a sudden that becomes more complicated, and if you do something like x plus 2 to the 100th power, it becomes more complicated yet. Surprisingly though, with our powers in a complex number, it's actually not very complicated when you raise something to some power, and you'll see that in a second. Like we're going to go through kind of an example of where we're going to do something cubed of this power, or this polar number here. And so when we cube something, that means that we're going to take that thing and multiply it by itself 3 times. And since we have a product then of 3 different things, we can treat this as some product here multiplied by some other polar number. So I'm going to do this part first. If I'm ignoring this section and I'm going to multiply that by it later, I'm going to focus on just doing a power, or doing the product rule, the product theorem with our polar numbers and those two. So yesterday we learned that we do the R1 times the R2, so 2 times 2 is 4. And then to combine it into one power then, sorry, not power, to divide it into one polar form here, we add up our 2 angles. So 10 and 10 would be 20. So I can replace this of 4 cis 20, and that's still getting multiplied over here by 4 cis 10. And then I can use the product theorem with those two now. So this is now my R1 and R2, so I'd have 4 times 2, which is 8. And then I again would add up our power, or our angles here, so I'd have 20 plus 10, which is 30. And if I had another one, then I would multiply that by it, and I'd have this times, 2 cis 10 again, and I would add up my powers, my polar angles, and I would get 40 in that case. And so we can keep going and keep going, but we'll notice a pattern of what's happening every time that we put in a new power there. And if we're raising this to the 3rd power, we can notice that we are getting 8 because it's going to be 2 times 2 times 2, which gives us 8. So that'll be 2 to the 3rd power. And then how we got 30 is that we had 10 3 times, that we ended up using the product theorem that we saw yesterday. We just end up adding those angles. So that would, since we had 3 of the angles, we added up 10 3 different times. So we could write that as like 3 times 10. And we notice like that is really the power that we're dealing with. So if we're going to generalize this and have any r to the nth power, then we know that we're going to have that value r, which is 2 or 5 or whatever that case is, and raise it to the nth power because that's how many we're going to have in our line. And then the other way that power plays in, or comes into play, is that's how many times we're going to add in that theta. So it ends up being n times theta. So that makes it like way easier to deal with if I have this like power rule that I can just kind of separate it in this way and just like take that n and multiply it here on the inside of our theta. That makes our raising something to some power way easier to deal with, because if I had something like 2 cis 10 to the 100th power, then that is something really hard to do, but it's a lot easier to do 2 to the 100th and then cis 10 times 100. Like that's way easier to deal with than doing something and multiplying it out 100 different times. So this is called De Moivre's theorem, where we can make our powers a lot easier to deal with in our polar and our complex number system form. So the first thing that we're going to do in any of these cases, since it's easier to deal with it in a polar form like we have here, to use de Moivre's theorem, we have to have it in a polar form. So that's what we're going to do for our examples. When we have something like this to the 8th power, we could start by expanding all that out. Like we could do 1 plus I root 3 times 1 plus I root 3 times 1 plus I root 3 times 1 plus I root 3, and you'd get something that's really crazy. It would take you forever to simplify, but if I just put it into, and use de Moivre's theorem and put it into polar form, this would have a real component of 1 and an imaginary component of root 3. So here's our vector here. This is a 30, 60, 90 triangle. Our R value is going to be 2. This angle here producing the root 3 is going to be 60. So I could rewrite then this complex number in polar form. This is in rectangular form now. But I can rewrite it into polar form as 2 cis 60. And then I'm raising that to the 8th. So if I'm going to use de Moivre's theorem, this is telling me that I can bring down the power and raise then 2 to the 8th, because that would be what I have in a line here, 2 to the 8th power. And then I can multiply 8 by my angle. And I'm doing that again because I have this in a line, and I end up adding all of those degrees, those angles, as I'm using my product theorem. And so I'm going to be adding it 8 different times. So it's just another way of saying multiplying. Okay, I'll do 2 to the 8th in my calculator, and you get 256. And 8 times 60 is 480. And we're asked to answer this in rectangular form, so we need to go back to this with our real component and our imaginary component. I'm going to come up with a coterminal angle, so I'll subtract 360 just so I'm dealing with something that's a little bit easier. So that would be the same thing as a cis of 120. And then I can use that to come up with my direction and my R value and look at my real and imaginary components. So 120 degrees is going to be in quadrant 2. That's dealing with a 60-degree reference angle. My R value is 256, which is a large number to deal with, but remember, like, it's really not that hard to deal with those once you come up with your 30, 60, 90 relationships. That's our hypotenuse. We always have that the short leg that's half of our hypotenuse. So if I do 256 and divide it by 2, you get 128. So that's this angle, or this side length right here. And remember, we're in quadrant 2, so that should be negative. And then this side length should be that short leg times root 3. So 128 root 3. So altogether, in rectangular form, I have a real component of negative 128 and an imaginary component of 128 root 3 I. So again, like this answer really is this thing to the 8th power, but it would take us like way too long to represent it that way, to actually write out and come up with all of those, all of like the 1 plus I root 3 times itself 8 different times and expand it all out. It's way easier to use de Moivre's theorem, change it into polar form, use the de Moivre's theorem, and come up with that conversion back into rectangular form from there. Okay, one more before we move on to our roots. So again, this would take way too long to expand out, so we're going to change it into polar form first. So we have a positive root 3 and then negative root 3 for our real and our imaginary components. So I'm going to write that out here. We're going to be in quadrant 4. This is a 45, 45, 90 triangle. Our hypotenuse then in a 45, 45, 90 relationship is x root 2. So it'd be root 3 times root 2, which is going to be root 6. And our theta value being in quadrant 4, so root 6 is our R, being in quadrant 4 would be 360 minus 45, which should be 315. And that's to the 5th power. So again, de Moivre's theorem says that we take that R value, we raise it to the power that we are raising our entire rectangular form into. So this case, root 6 to the 5th power. And then we pull that 5 down, we multiply it by our angle. So root 6 to the 5th power means, and I'm going to write it out this way just because I actually want it as a real answer, like an exact answer. So this would be root 6 times root 6 times root 6 times root 6 times root 6. And you don't have to show this work, but I'm just showing this as a visual so you can get the hang of like how these powers work and reducing them. So I'd have root 6 times root 6, which is 6. I'd have another section, root 6 times root 6, which is another 6. And then I'd have that leftover root 6. So altogether that would be 36 root 6, 6 times 6, and then the leftover 6. In my angle here, if I do 5 times 315 degrees, I get something really large, 1,575. And that's too much of an angle to deal with, so I'm going to keep subtracting 360 degrees until I come up with an angle that's more manageable, something that I can deal with a little bit better. And eventually, as you keep subtracting 360 degrees, you'll get 135. And that's on our unit circle. That's something that we can use to write into rectangular form. So 135 degrees is here. That's a 45-degree reference angle. Our value here is 36 root 6. And then we go backwards, like here we multiplied by root 2, but we're going to divide by root 2. And when we take this and divide by root 2, just like here when we multiplied root 3 times root 2, we got root 6. So when we divide by root 2, it'll end up being root 3 again. So this will be negative 36 root 3, and then positive 36 root 3. And again, you can like just double check that if you go forward in the forward direction and multiply by root 2, 36 root 3 times root 2 is going to be 36 root 6. So you can use that to help. And again, we're in quadrant 2, so make sure that's negative. So our answer should be 36 root 3 for our real component and our imaginary component of 36 root 3i. So that's the first part, just raising things to certain powers. You handle those powers by using de Moivre's theorem. The other thing that we're going to do in this lesson is talk about roots, which is kind of dealing with a certain type of power. But to do that, we have to review a little bit about what the fundamental theorem of algebra says. You might not even know that this is called the fundamental theorem of algebra, but you kind of know what this says. So when we talked about quadratics back in chapter 6, when we were talking about like the number of solutions for certain equations, we kind of mentioned this. If I was having something to like x squared, I would know that there's a potential for 2 solutions. And if I have something like x cubed, there's a potential of 3 solutions. And in the real number system, it doesn't have to be 3. Like we could have like a double root or a repeated root that only shows up once. But in every number system, then we actually do have the number of roots or the number of solutions equal to the order of that equation, which is really just the power. So the order of the equation, or I'll write it this way, power of the equation is equal to the number of solutions, the highest that we have. So it might not mean that all of them are real solutions, but we're dealing with complex numbers now. So if I have something like a repeated root, like maybe you know, x squared equals 1, we know that that has 2 solutions because when we take the square root, we get plus or minus 1. But like x cubed equals 1, when we take the cubed root, we only get the positive version of 1. But that means that we have 2 imaginary solutions out there. So we have real solutions, and then we have imaginary solutions that go along with it. Our real solutions that we end up with will be real solutions on our number system, or like we're going to still write it with in a complex number way. So it's not like you have to like know how to do that or how to do these separately. But the idea then is that like we're going to be using de Moivre's theorem and like coming up with where those imaginary solutions are located then, or like how to represent them as a polar number in our complex number system, along with our like real numbers. So to find our roots, we have a set order of things that we're going to do, or a set procedure. So the first thing we're going to do is isolate the variable. So we're going to do that like normal with the exponent before we like come up with a power. Then we are going to convert it into polar or trig form. So like the r cis theta That's what we're going to do. Then we're going to use Neumov's theorem. So it'll be something to some power. So we're going to represent it this way. So we have like our polar form to that power, just like we did here. We converted it into our polar form. And then we're going to set our corresponding parts equal to each other. And we'll solve. So that means solve like our R value, and then we're going to solve for the theta value. And the key here is that when we use Neumov's theorem, we have like n times theta. And remember that n there, like if it's 2 theta, that means we go 2 times around our unit circle. So that's kind of talking a little bit about chapter 6 when we had 2 theta. We ended up adding 360 to each of our solutions and then dividing. That's what we're going to do here too. Okay, so this is the idea. We'll go through kind of a generic example of finding the cube roots of 64. So that means that if I'm finding the cube roots of 64, that means I was dealing with some cube that equals 64, and then I'm looking for then the cubed root that would give that x, or what x value would give 64. And you might know, like right now, that one of your answers is going to be 4. That again is only one answer. This fundamental theorem says that the order that we have, the order of the equation, which is the power, is equal to the number of solutions. So this should have 3 solutions. One of them's real, 4, but 2 of them are imaginary solutions. So how we're going to tackle this, how we're going to find both the real and the imaginary, you don't even have to do anything separate, like we're going to find them all at the same time, is to convert this into a polar or trig form. And so that means that we're going to represent like x equal to something that is in some polar form. So really all that means is I'm going to take x and I'm going to say that that represents some imaginary or some polar number. So that would be r cis theta to the 3rd power. And then I'm going to convert this real number into something that is in polar form too. And if this is some vector, that means that I'm on the x-axis at 64, that would be my x value, and 0i for my y value, my y component. So to represent this as a polar component with the direction, my r value, my magnitude is 64, and then my angle of my direction is 0. So I'm on the x-axis. Then we use Neumov's theorem on this side because we have something raised to some power. So that tells us that we bring down the power and like cube the r value, and then we bring down that power and multiply the theta by that power. So we're through step 3, and then we set our corresponding parts equal to each other. So r goes with 64, so r cubed equals 64, and then 3 theta equals 0. So let's deal with this first. If we're looking for the cubed root of 64, you can do that in your calculator. If you like, there should be either a cubed root button, or if you can't find it, like either Google it somewhere, or you can ask me tomorrow and I can help you. But we're going to find the cubed root, which we already knew was 4. That's our r value. For this side, to solve for our theta value, we would divide by 3, but remember that this is going n times around their unit circle, so we have to find 2 coterminal angles with this, so we have 3 solutions in total. So one of them is going to be 360, and then we add 360 again for our next coterminal angle, which is 720, and then we divide everything by 3. So 0 divided by 3 is 0, 360 divided by 3 is 120, and then 720 divided by 3 is 240. And this represents then all of our solutions that are the real solutions and the imaginary solutions. So if we like make this into a polar number, having an r and a theta value of 0 would be 4 cis 0. The next one would be 4, an r value of 4 and a cis value or a theta value of 120. So that would be an imaginary number. And then 4 cis 240. So that we have 3 solutions for our cubed root for the 3, the order of the power that we're dealing with. Now this you know is the real number, because that would be on the x-axis with that magnitude, just like 64 was 64 cis 0. That's our real solution, and then these two are the imaginary solutions that come from finding the cubed root, so that we actually do have 3 answers to our original question. Okay, same idea. We're going to find the cubed root of 8 cis 135. This time we're not having a real answer, so we're going to have all imaginary solutions for this. So again, we're finding the cubed root, so we're going to start with x cubed. And then we're going to convert it into a polar form. So this side's already polar. Awesome. This side's not, though. We want to take this x and we want to replace it with a polar number. And then we use de Moivre's theorem, so we pull down the power for our R value, we pull down the power and multiply it by theta, so we get the same thing that we just went through in example 3. And then we set our corresponding parts equal to each other, so R cubed is going to be equal to 8, and 3 theta is equal to 135. Remember, though, that on this side, when we deal with that 135, that's only one of our solutions for going the first time around our unit circle. But we have to come up with 3 solutions on this side. So we need 2 more coterminal angles. So I'll add 360 and then add 360 again to get our values of 135, 495, and 285. Or sorry, 855. And then we solve these both, this one for r and this one for theta. So when I take the cubed root of 8, I'll get 2. When I divide all these things by 3, the first one, when I divide 135 by 3, I get 45. The second one, when I do 495 divided by 3, I get 165. And then 855 divided by 3 is 285. So again, these represent all of my solutions. R theta, R theta, R theta. So 2 cis 45, 2 cis 165, and 2 cis 285. So that's a general principle. It's a general kind of process to solve for them. So we're going to do 4 more examples. We're going to go a little bit quicker on these ones just because we know kind of what we're doing now. So this is the same process. We're finding the cube roots of this rectangular thing. So the first thing that we have to do after I write out what the problem is really asking, find the cubed root, means we're solving for x when x is x cubed. And then we convert everything to polar. So we're going to convert this to polar. And to convert this rectangular coordinate to a polar coordinate, we're going to draw a diagram. So it would be -5 root 3, -5. So we're down here in quadrant 3. -5 root 3 is my real component. -5 is my imaginary component. So this will help me get my direction. This will help me get my, my R value. So this is a 30, 60, 90 triangle. My 60-degree angle is across really from my root 3. So this is my 30-degree angle, which means that my 30-degree angle across from that, to get to my hypotenuse, I double it. So this should be 10, and then I should be dealing with the angle of 210 degrees. So this whole thing will be 10 cis 210. And then on this side, when I convert it, it'll be r cis theta cubed. Now we use de Moivre's theorem. So on this side, I'll have r cubed cis 3 theta. I don't know why I put these in parentheses. I didn't need it. And then we set our corresponding parts equal. So we'll have r cubed equal to 10 and 3 theta equal to 210. Let's find our coterminal angles. So add 360. We get 570. Add 360 again, we get 930. For this one, when we find the cubed root, this is not something that's a nice number, so I'm just going to leave it as the cubed root of 10. That's fine. On this side, I can divide everything by 3. Our first one will be 70. 570 divided by 3 is going to be 190, and the last one will be 310. So again, this represents our three solutions, r and this theta, r and this theta, r and that theta. Our r being like cubed root of 10, we're just going to leave it like that. We're not going to simplify it. We're not going to write it as a decimal. And we can use that to write out our three solutions. Okay. Good. All right, enough with cubed roots. We've been doing that a lot. I guess we do it one more time, or two more times. For this one, it's a fifth root. So the first thing, like this is a little bit different from the other ones because it's not, well, first of all, it's not saying like find the fifth root of 1. It's written as an equation. So the first thing we're going to do is solve for your variable. So I'm going to add 1 to both sides. And now we have something that looks like what we set up for example 5, like we have x cubed equals something. So now we're at the convert everything to polar form part. So this is r cis theta to the 5th power. And on this side, this is a real number that's on the x-axis, direction of 0, magnitude of 1, so that would be 1 cis 0. Oops, not theta, 0. Sorry. Okay, and now we use de Moivre's theorem, so r to the 5th cis 5 theta equals 1 cis 0. And we set our corresponding parts equal to each other, so r to the 5th equals 1, 5 theta equals 0. But then again, we're going around 5 different times, so we have to add 360 to get our 5 answers. So we'll keep going. Add 360 again, we get 720. Add 360 again, we'll get 1080. And finally, last time, add 360, we get 1440. And then we'll solve for r, we'll solve for theta. This time when we take the 5th root of 1, that's just going to be 1. You know that you will have a real solution for this, like 1 will be a solution, which is what our first one is. R value of 1, theta value of 0 gives that one solution, but then all these 4 solutions will end up being the imaginary solutions to give us and make us up to 5 solutions. So if we divide this by 5, we get 72. If we divide 720 by 5, we get 144. Divide 1080 by 5, we get 216. And divide 1440 by 5, and we get 288. So we'll have 1 cis 0, 1 cis 72, 1 cis 144, 1 cis 216, and finally 1 cis, not R, 1 cis 288. 5 solutions in total. That's one way to check, because if you only end up with 1, like that's the whole point of this thing is you need 5. So if like you forgot that you needed the coterminal angles, you'll probably remember really quick when you only end up with 1 solution. You should have 5. So make sure that you go back and count. Okay, last 2. For this one, again, we have to isolate our x value. So I'm going to move the I over to the other side. And then we're in the part where we convert to polar. So this will be r cis theta to the 3rd power. This one we haven't dealt with before. So negative I, it's the same kind of idea as we dealt with like 0 or real numbers. Negative I means we have no real component, no x value, but negative 1 for our y component, which means that we're looking or having a direction going down, and our angle here is going to be 270 degrees. Our magnitude, even though this is negative 1 for our y, our r value, remember, is always positive. So our r value is going to be 1, and this angle is 270 degrees. Now we use de Moivre's theorem, so r cubed cis 3 theta. And we set our corresponding parts equal, so I have r cubed equals 1, 3 theta equals 270. And then I find my coterminal angles, add 360, we get 630, Add 360 one more time, we get 990. And we solve for r, we solve for theta. If we take the cubed root of 1, we'll get 1. If we divide everything by 3, we should get 90. 630 divided by 3 is 210, and this will be 330. So we get, finally, 1 cis 90, 1 cis 210, 1 cis 330. Okay, last one, and then I'm done talking. Our last example is like pretty similar. I just want to make sure that we're all set and like actually writing out our form, our polar form for stuff that's just like a number or negative I. Like sometimes that trips us up, even though we're like really good at writing like now writing this stuff in polar form, like sometimes just writing like negative I like gives you pause, and it's because it's so simple, it's on our axes. So again, we need to solve for our variable first. So we solve for x cubed. This we're going to represent, now we're at the polar, change to polar form. This we're going to represent in polar form. Here's our real component at -8. We don't have an imaginary component, so we're on our x-axis. So our x value here is -8, but our r value, remember, is 8. That's our magnitude, the length of that vector. The way we get that negative, though, is with the angle. So when I represent this in polar form, it'll be 8 cis. The angle that I'm going to the left here is 180 degrees. On this side, we'll have our cis theta to the third power. I'm going to jump ahead and write that with de Moivre's theorem. So I'll have r cubed cis 3 theta. We'll set all of our parts equal. So r cubed equals 8. And we'll have 3 theta equals 180. 180 plus 360 is 540. Plus another 360 for our coterminal is going to be 900. So r equals 2 for that one when we take the cubed root. And when we solve for all of our theta values, we should get 60, 180, and 300. And we match up again with our, all of our answers. So we'll have 2 cis 60, 2 cis 180, and 2 cis 300. And just so you know when you're looking at this, because this should actually have a real solution, you can take the cubed root of negative numbers. This one is actually representing our real solution, because if I drew out like the component of this, I'd be at 180 degrees, which is on our x-axis. Our x value would be negative 2, and I'd have plus 0i. So this is our real number, -2. All of these ones have some real component and some negative and some imaginary component, because I'm not at like an axis, specifically not at the axes of 180 degrees or 0 or 360 or whatever. So this is our real one, but these two are then going to be our imaginary solutions.